All right, we're going to shift from AI to quantum. We have Kate Marshall from IBM.
Can you hear me? Yeah? Yep. Okay, cool. Okay, so yeah, my name's Kate Marshall. Lovely to meet you all. I'm going to be talking about something called quantum-centric supercomputing today. Now, I do come from a corporate, so I do have to say a lot of these fancy lingo words all the time, but you can think of this as quantum plus HPC, just for the purpose of this talk. So we're going to talk about quantum-centric supercomputing, which, to be honest, isn't something that's been regularly realized yet. It's something that people are thinking about a lot. Quantum is still very much a technology that's in a immature phase of research and development, and we're still seeing sort of major breakthroughs being sort of demonstrated for sure, but we're not there yet. So we're going to talk about a little bit more in detail about where exactly we are. But just to give you context as to where I'm sitting in this, I'm a research application engineer, so I look at near-term quantum computing applications. So this involves things about how to make quantum computers useful today, even though they're not mature. I end up speaking a lot to clients throughout sort of different advocate roles that I hold. So I do actually speak to customers regularly about what their ambitions are for quantum. So that puts me in a nice position where I'm sort of hands-on with the technology, but I can also speak to clients about what their needs are. So definitely this is a work in progress. If you notice things that you want to talk more about, I'd love to hear from you. And yeah, let's make this as interactive as possible. I'm sure there probably sounds like we're running a bit tight on time, so maybe we'll have time for some questions at the end. But if we don't have time, then please do just come and find me. So sort of context of what I'm going to cover. We'll talk a little bit about the motivation for quantum computing. We'll talk a little bit about what people are actually using these machines for right now. But then we're really going to focus on this point of where are we today, what's the sort of major breakthroughs that we're listening to now, and what does the future look like when we start to integrate quantum as part of a larger sort of supercompute workflow that doesn't just, it's not all about quantum, but it's actually about using quantum as a tool in collaboration with other cutting edge supercompute technologies to solve the world's hardest problems. So to start on that first point about why we're interested and sort of why is quantum computing important, we need to think about this as a technology that works fundamentally differently to any other type of information processing that we've encountered to date. So with quantum computing, we can take advantage of the fundamental principles of quantum mechanics that you may or may not have heard of, like superposition and entanglement. I'm not going to bore you with a physics lesson as to how these terms work, but at sort of a very high level, we can think of these as why we use these concepts is because we want to be able to create problem spaces, which if you're interested and you want to read about it later, they're called Hilbert spaces. They're extensions of the three-dimensional space that we live in, but they're far more complicated than what we can create with any equivalent classical computing technology. So we're using these concepts of quantum mechanics to be able to create problem spaces that are hugely more complex than anything we can hope to obtain classically, so that we can start to address problems that are considered classically intractable or impossible to solve within any reasonable amount of time using even the most powerful classical supercomputers available to us today. Now, very specifically, and something that I think is sort of represented sort of clearly, maybe, I don't know, it may make some changes to this slide, but what we're trying to represent with the diagram on the screen is that, yes, there are a lot of problems that would be considered NP hard or classically intractable with even sort of really large supercomputers we have accessible today. And there's a small subset. So the first thing is to think about the fact that we're not trying to address every classically difficult problem with quantum computing. In fact, we're just trying to look at a very small subset of problems that satisfy a strict set of predefined conditions that we hope to see some advantage of if we combine the powers of classical and quantum compute. So there's a small set of problems that we call BQP problems that we're trying to look at with this technology. But just to be super clear, there's just as many problems that are really, really hard for quantum computers to do. So in sort of this context, we need to remember that although people, you might read in sort of the newspapers or whatever, that quantum computing is going to change the world and revolutionize everything, and we're not going to need classical computers anymore, and when am I going to get a quantum computer on my phone? Actually, quantum computers are not that good at a lot of stuff. They're very good at the very specific tasks, but we would never envision a world where quantum computing eradicates the need for classical computing. We very much see this as even in an era of quantum advantage, which is this point in time where we can see a practical benefit delivered by these quantum computers over and above something that we can see obtained or achieved with classical computation today. Even in that era, we really see classical and quantum computing working hand in hand with one another. So what sorts of problems can we do with them? I've sort of stressed the point of let's remember they can't do everything, but the the types of problems that quantum computers are really good at generally sit in three distinct categories, and they're sort of visible on the screen right now. One of them is simulating nature, so that might be looking at sort of low-level chemical interactions between different molecules in a pharmaceutical context. That might be with the goal of sort of trying to look at novel ways towards drug discovery. If you're in a company that's looking to make more efficient batteries, you might be looking at the sort of the interactions between lithium compounds for making more efficient battery materials for use in phones or electric cars. Another different type of problem that quantum computers are very good at is sort of maths and processing data with complex structures. So this generally falls in the family of machine learning problems. A lot of the concepts that underpin classical machine learning, we can actually sort of extend and build upon and look at in fundamentally different ways using quantum kernels and various different methods as well. So quantum computing can actually enhance a lot of machine learning processes that we're already familiar with. And then the final category is search and optimization. So that could be things like looking at portfolio optimization in the context of what financial services might be interested in. If you're a company that's looking at shipping units or containers from one side of the world to the other, you might be looking at routing optimization problems, things like that as well. And you can see a list of the sorts of clients we're working with. On the sort of list there, that might be a bit too small for you to read, but as a couple of examples on this slide and so hopefully more readable text, we've got sort of a couple of taster examples of who the real clients that we're working with on these different use cases are. So for example, E.ON was the first energy company in Europe that sort of really I would say, onboarded with this technology to explore some different interesting applications. One of the use cases that they're looking at includes things such as trading energy units across market borders and the sort of optimal procurement of energy across on the like spot price day ahead and on the day energy market, so that you can try and sort of optimize the distribution of energy across a continent. They're also looking at fraud prediction and various different sort of machine learning problems and pattern recognition problems there. They're also looking to see if they can predict faults in their energy network, and also looking at things like sort of optimizing large-scale energy network grids, which is arguably one of the most important problems and for our generation is how do you optimize a large-scale geographical energy network grid, and it's something that a lot of different energy providers are looking into just now. Kind of, I guess, a UK focus one would be we work specifically with the Science and Technology Facilities Council, which might be of interest to people in this room. We have a joint research agreement with the Hartree Centre. So we work very closely with colleagues up in Daresbury, where we look at various different sort of industry applications, and we actually we do sort of short-term projects where we'll take a project from a client. We have access to AI, HPC, and quantum specialists, and we'll try and break down the problem in the best possible manner for the problem at hand and try to look at the different technologies that are most suitable and try out different things. And we do sort of run real hardware experiments using those different technologies for different industry applications. And that's through a program called HNCDI, or the Hartree National Centre of Digital Innovation. So if that's something you're interested in too, we'd love to speak to you after. So I promised we'd talk about sort of where we are, what the state of this technology is, and then also the story of sort of where does HPC come in, where do we see this technology going in the future. So this first term, I'm going to go through all these different complicated pieces of lingo that we have on the screen just now, but first of all, we'll talk about quantum utility. So utility is an interesting term. I sort of alluded to a similar term earlier, which is this term of quantum advantage, and that's the point in time where we expect to see a tangible benefit demonstrated by quantum computing over and above anything that we can achieve with classical computing today. We have not achieved that yet, and that is probably something that you might have read about in the news. A few people sort of claim that they have or they haven't, and it's something that will be a major breakthrough in our industry. But I actually like to think about the timeline of how we see this technology emerging and growing over the next few years as broken into three key phases. The first one being the phase that we're in right now, which we generally call today noisy intermediate scale quantum computing. So that's where we are just now. When somebody demonstrates quantum advantage, it will not be that we've demonstrated quantum advantage in one application and now we can expect it to be applied to every problem we've ever tried to use quantum for before. No, absolutely not. what we'll see happen once we've demonstrated quantum advantage for one type of application in one research domain, we'll actually then see over the next, I imagine, 10 years or so, that same demonstration or iterative examples of quantum advantage being demonstrated across lots of other applications and research domains. So the era that we'll be walking into will not be one point in time, but we will be a sort of a phase of different experimental demonstrations of quantum advantage across all the different research domains that are interested in quantum. After that sort of quantum advantage era, we'll then see the third era that I'm sort of alluding to just now in the way that I sort of imagine this in my head, which is what we call fault-tolerant quantum computing. And that will be when we're able to sort of demonstrate error correction or error-correcting quantum computers that are able to sort of, we build in a physical way that we're able to account for natural errors that we already know and expect to see in these devices, but in a similar way to how our classical hardware and computers are error corrected today, we hope to do something somewhat similar in sort of building in redundancies to our quantum computers in the future so we can use them at scale in production systems. So I guess if you can imagine that timeline just now, we're fairly early on. We're just before the quantum advantage era, but it's not been demonstrated yet. And quantum utility sort of basically captures that point in time where we are right now, which sits immediately before quantum advantage, but distinct to. So the key thing that if you were to walk away with one thing today, I'd hope it would be that quantum advantage is not something that's been demonstrated, but what quantum utility describes is usefulness before this idea of fault tolerance. So how can we make quantum computers that are noisy and immature, and we're sort of not trying to exaggerate anything beyond what we can achieve, but actually this near-term research is exciting because we can do useful things and use these quantum computers as a tool for science today, even though they're not fault tolerant, which is really cool. And the way that we do that is by combining them with other cutting-edge compute technologies like HPC. So quantum utility basically describes high-fidelity quantum computation outside the reach of exact classical simulation methods. And this is very vague, I think, but basically, I think if you look at this term from what we actually see in the literature, over the last sort of, I guess, 10 years, maybe more, well, probably more, what we've seen is the quantum computing research domain trying to prove that they can do the same things that classical computational scientists can already do. So if we were to think about who was leading the charge and who was chasing it, it was always the classical computational scientists out in front and quantum computational scientists trying to demonstrate they can do something similar. The narrative change that we've seen in the last year, which sort of constitutes this idea of quantum utility, is that quantum computers are now starting to demonstrate something that's going just beyond the edge of what we can classically simulate. So we're starting to be able to do chemical calculations or look at the low-level properties of different molecules at a level that we can't classically simulate to an exact level. The difference between that and what I'm calling advantage is that we can actually replicate these results using really highly specialized approximate methods that I definitely don't want to discard. But the exciting thing that kind of shows just how close we are to this idea of quantum advantage is we're going beyond exact classical simulation methods, which is really cool. And the only way that we're able to do that is by bringing in really cool software techniques, some hardware tricks, and bringing together the power of HPC and quantum to demonstrate something that none of those technologies could have demonstrated on their own. So it's the power of all of them coming together that's sort of making this possible today. So last year, IBM demonstrated this with this sort of paper that made the front cover of Nature and was very exciting for all us researchers internally. But basically, we were able to do some chemical calculations beyond exact classical simulability. And what we've seen is that this has been started to be replicated elsewhere in the industry. So we're starting to see this term, utility, being used in the literature elsewhere, but also we're starting to see these utility scale experiments being demonstrated elsewhere. And some things that you can kind of point out as patterns of what each of these papers are doing is they're usually, I guess one of the features that you can actually see on this slide is most of the circuits they're running are using more than 100 qubits. That can be physically mapped to something that wasn't really possible 5 years ago because we didn't have the physical scale of devices that could support those kind of experiments a couple of years ago. So that's definitely something important to note. But also a lot of them are, I mean, if you actually read the papers of how they're able to demonstrate these things, it's because they are using really cool classical software techniques to help correct for errors that they understand and know exist, but that we can sort of mitigate for at a hardware and software level using these sort of error mitigation and error suppression techniques we have available today. So what comes next? So we're at this sort of quantum utility point in time. We hope to see quantum advantage demonstrated in the next couple of years. If we look at, oh, no, damn, I didn't have the slide that I wanted there. If we wanted to think about sort of where we're going with the actual pieces of hardware that we have, we see that the scale of devices is going to continue to be delivered over the next few years. In fact, I think I should have the slide that I'm looking for a bit further on. There we go. Again, not very easy to read. But what this is showing you is basically a track record of all of the different processors that just IBM have delivered over the last few years. This is really important because it basically documents sort of what we expect to be able to do in the next couple of years, but also we can see from the current tick points on this map that we have delivered all of these milestones to date. So it means that we can actually start to predict what science we can do with these processors, which is pretty cool. So as we're sort of, I guess in 2022, we released the first processor with more than 127 qubits. One of the key things that sort of I mentioned comes together when we're able to demonstrate these experiments beyond the reach of exact classical simulability is how we're actually going to match the scale and the increasing size of these devices with other types of, I guess, techniques to be able to use this as a tool for science that's not just all about quantum, but actually part of a larger ecosystem of things we want to use to be able to address the world's biggest problems. And this is where this idea of quantum-centric supercomputing, or HPC in quantum, comes into play. So there's three key things that we think is interesting when we talk about HPC and quantum, and they're sort of listed on the screen right now. One of them is modularity, one of them is communication, and one of them is middleware. So modularity of quantum computing, if you can imagine that roadmap I showed you before, we have this increasing sort of device scale and size that we've been demonstrating sort of year on year. But one of the sort of key things that becomes a real physical challenge when we're sort of building these devices is the infrastructure that supports them. So one of the things that was really exciting last year that we were able to demonstrate was these new versions of how we scale our dilution refrigerators that host these devices. So this is a picture of IBM Quantum System 2, which is one of our first sort of like modularly scaling physical devices where we have sort of the one fridge supported by multiple of these little cuboids you can see sort of placed on the outside. And you can sort of imagine how you might connect multiple fridges together, and that includes sort of, if you can imagine that each of these fridges might be hosting one, if not more devices, we can start to see how in a data center we could physically see these this infrastructure scaling in a way that we couldn't really demonstrate before. Beforehand, we'd only ever seen one device held in like sort of one fridge, and we couldn't really imagine how that sort of horizontal scaling could be physically manifested when it came to quantum. So this was a really exciting development last year. And as you can imagine, it had implications for how on earth we were going to sort of create the technology that would support these devices. We had to for example, with one of the devices we released last year, it was more than 1,000 qubits in size on one device, which was really cool. But rather than just sort of thinking about that vertical scaling, when we start thinking about horizontal scaling and thinking about more sustainable ways that we could scale in the future, we came face to face with a lot of the technical challenges of what happens when you fit the maximum number of qubits that you can on one processor. We had to connect over 1 mile of flex cabling because every single one of those processors needs to have a separate input and output signal, which is a physical flex cable that we attach to those qubits. So when we had more than 1,000 on one device, we had more than 1 mile of flex cabling on a device that was probably like the size of a textbook. So it was really starting to see like why we had to start thinking about the bigger picture here and think about modularity of the infrastructure supporting these devices. Next up, obviously, we sort of mentioned that when we think about that horizontal scaling, we need to be able to have modular infrastructure, but we also have to start thinking about addressing some really cool physical challenges that we're working hand in hand with different sort of universities to try and answer, which is how do you maintain the quantum states between physical fridges? So how do you long range and tangle different devices so that you can run computations across multiple fridges? This becomes a lot more complicated in a quantum context because the quantum state that you're trying to preserve is so sensitive anyway. You're already exposed to so much noise that makes that state vulnerable. How on earth are you going to do that long range? So we're working with University of Chicago and University of Tokyo to try and address that sort of Quantum Communication Challenge. And last year we released one of the first devices, which is this Heron device at the very bottom of the screen, which was how we sort of demonstrated this at a really small scale, but we really want to be able to create these couplers that can attach multiple devices together and maintain quantum states at long ranges so that this can be supported in a sort of data center environment as well. The very last thing I'll cover is middleware, which is basically we can think about as software for quantum, and that's how can we orchestrate these workloads from a software perspective so that data scientists or HPC researchers don't have to necessarily, be sort of quantum computational scientists in order to be able to use these machines. I myself come from a physics background, but I have seen the pain of what happens when you let physicists build all the software around quantum computing, and I don't recommend it to a friend. It's definitely something that I wish we'd addressed earlier and we're starting to see the pain of now. But basically, when we think about what we'd eventually like to see the future of quantum computing look like in the future, I really, really hope that it's not just quantum physicists. I really hope that it's industry experts, that it's people that are familiar with their industry domain and just want to use quantum computing because it's suitable for the problem that they have, and that we can build layers of extrapolation between the hardware and the user so that they can use this technology without having to go and get an extra PhD first, because that's obviously, like, I guess any software engineer's goal is to do software so well that they make their role redundant, and that's hopefully what we're going to be able to do with quantum as well, is we'll be able to build software that sits in between you and the hardware so that this technology is as usable as possible, and you don't necessarily have to understand what's going on at a really low level unless you really want to, and that's perfectly fine. But we need we've got plenty of people with the industry domain of how to build these chips and what we want to do in terms of the scaling, but what we don't have is a lot of people telling us what sorts of problems we might be able to use this for, and making sure that those same people can use this technology. And that's where the software comes in. So what we can see on this sort of image right now is this first sort of, with the laptop open, you can see Qiskit featured on the screen there. Qiskit is, first and foremost, it's a software development kit for sort of building programs at the layer of sort of circuits and even pulse levels if you're sort of interested and come more from a physics domain. It's a Python-based software kit for defining your problem in a programmable language that you're probably already familiar with. However, it just sits at the front of this image. So there's a lot more that goes on in between the laptop and when the problem meets the hardware. So this middleware for quantum is basically in charge of this idea of taking a problem that ideally would probably be some really, really big problem in the future that can be broken into subroutines where each individual subroutine, one of them might be relevant for quantum, but the other ones might not be. Some of them might be more relevant for a GPU, some of them might be more relevant for a CPU or whatever else. And this middleware is meant to be the sort of intelligent orchestration layer that divides up a problem and assigns it to the most appropriate sort of hardware that makes sense for the problem at hand. So this is definitely sort of a work in progress. It's something that we're sort of proving out right now, but we're also working with the industry and with a lot of sort of HPC research centres to try and understand how best to do that. As you can imagine, when we sort of talk to HPC data scientists, etc., a lot of their questions is like workload management and how we can schedule different sort of problems to work across QPUs and GPUs and CPUs, etc. We're trying our best to sort of make sure that we're not sort of putting too many barriers to entry at this point in time. So we're trying to like face that head on as early as possible on the workload management side. Once you've decided that there is a part of a problem that's relevant to a QPU, it gets passed to something that's sort of sitting towards the back there, which is something called Qiskit Runtime. So Qiskit Runtime is essentially, it's a classical software stack that sits physically close to the hardware. So that's a sort of containerized orchestration layer that's managing sort of which pieces of your problem need to be run on the hardware and when. So if you have an iterative problem, which might have, for example, you're going to optimize some parameters, and every iteration of your experimental run, you want to update those parameters based on the results you got and then rerun your problem with a different parameter set. It'll be Qiskit Runtime, that classical software stack that's handling that and managing sort of any error mitigation or suppression techniques to correct for your results on that hardware. And then at the back there, we have sort of this elastic compute services represented next to the hardware. That's because Qiskit doesn't just support IBM quantum hardware. We actually support 8 different types of quantum compute hardware as well. This is, again, very sort of early phase technology of something that we're hoping to see growing in the next few years, but we're still all sort of in the game of figuring out what works. So last one from me is a sort of visual workflow of how this might work. So again, we've got a visualization of this person sort of defining their problem in a domain-specific language in a way that sort of makes most sense for them in that sort of number one that hopefully is visible on there. In sort of step 2 and 3, we're talking about decomposing that problem into parts, deciding which bits that are actually relevant for a QPU, and really understanding sort of which bits might not be as well, and how you want to deconstruct that problem so that we can only assign the correct parts of the problem to the quantum hardware. We then send those relevant parts of the problem to Qiskit runtime, which will then sort of be our classical compute stack that's orchestrating the running of that experiment on hardware. And then in step 5, we're reconstructing our results in a sensible way so that the user can sort of look at the domain-specific problem back in their domain language, and they don't necessarily have to be super familiar with the hardware or the physics of what's gone on at a lower level unless they really want to. And this is sort of, I just sort of put a screenshot here of one example of this, which was really cool earlier this year, which was basically another example of this utility before fault tolerance, but specifically this one was really cool because we partnered with Riken in Japan, and we were able to sort of run essentially 70% of the calculation workload on HPC and the last 30% on QPUs, so that we could actually do chemistry beyond exact classical solutions on this sort of quantum computing and HPC workflow. So just one example, and I really hope there'll be more papers like this in the future. But yeah, just one example of this coming to life. And I'll pause there. Is there any questions?
Kate Marshall, everyone. Is it a quick question? Okay, all right, I can do one question.
Hi, I've had limited exposure to quantum. I was working at Sixtera when Oxford Quantum put their 3 machines in, and our first use case was random number generation as a service, which is terribly mundane, but obviously very important for certain sectors. I'm an AI and ethics and compliance specialist. Is there any sort of nuances with quantum around the ethics and compliance that are different from traditional AI?
Yeah.
AI traditional.
It's a really interesting question, and something that, yeah, I hope will get talked about a lot more in the coming years as well. So I think probably in the UK it's something that I guess all of these different industries and standards bodies are trying to balance the gap between regulating too early and imposing sort of ethical commitments and things a bit too early so that we don't inhibit innovation, but also making sure that we're not sort of removing the possibility for that as we move on. So from a corporate perspective, IBM's internal view on this is that we always have a proportion of our devices available for free online. We run sort of events globally to make sure that we're sort of ensuring that opportunities and doors are open for sort of global markets, and it's not sort of focused on any one geography. But I do hope that sort of international standards bodies, and that I think those are really the industry organisations that will need to make a difference when it comes to sort of what happens beyond just what the corporates are doing. Because I guess there's only so far they can go before it then becomes, well, their opportunities are limited by continuing to do that. And so far it's really nice to see that IBM has continued to do that, even though it does make a massive loss for them. And they intend to continue doing that for however long we manage to keep going. But I hope that we'll see more international standards bodies trying to take an active approach to that, and I haven't seen that much yet.
Great, thank you. Thank you for the question. And if any others had questions for Kate, she'll be around in the break. That'll happen in about a half an hour. Thank you, Kate.
Cool.